Integrals have lots of other properties, just like derivatives have lots of other properties. Let's write some of them down. Properties of integrals, besides the fundamental theorem of calculus. One property that's kind of weird is that the integral of any function over what you might call a degenerate interval from a to a is always zero. Lines don't have area, right? I'm integrating from a to a. That's not really even an interval. I mean, my function might be continuous, but I'm like trying to find the area under the curve above 1 point. Well, it's not a region, it's a line, so it doesn't have any area. The integral is zero. Is that cheating? Is that something worthwhile to state? No, it's not cheating, and no, yes, it is worthwhile to state. Sometimes it comes in handy. It's really more of a definition than something you'd prove. It just makes sense to say this. Here's another thing that's really more of a definition. The integral from b to a of f of x, notice I switched the a and the b around, although that's just notation, is the opposite of the integral from a to b. But wait a minute, we've never talked about integrating over an interval going from right to left. Right? A is over here, B is over here. A is left to the left of B, it's less than B. So far, we've always been integrating from left to right, so to speak. Time is increasing, say. I'm saying you can define an integral from B to A, right to the left. It's like you're letting time go backwards. You're in a position in this day of technology to imagine time going backwards. Watch a video backwards. People walk backwards. Right? There you go. This is not something to prove. It's more of a definition. It's something that we define to be true because it makes sense. Why does it make sense? Think about the motion example. Pretend f of t is the velocity. Let's say this is A and this is B. And maybe this area is 10, representing, say, 10 meters. The integral from b to a of this function of t, this velocity, would be the opposite of the integral from a to b. So it would be negative 10. What possible application could that have? It could be a distance travel, or a displacement, I should call it, if you're watching the video backwards, running in reverse. When time runs forward, this is saying you're traveling 10 meters, or your displacement is positive 10 meters. You're to the right of where you started because you're always walking to the right. But you watch that video in reverse and you're walking backwards. The change in position is negative 10 in that context. That's why this makes sense for those kinds of applications. But it also makes sense in other kinds of applications as well. Third property is a simpler form of what I already wrote down on the previous page. This sum here. Let's write down a simpler form of that. The integral from a to b of a function is the same as the integral from a to c plus the integral from c to b. When you look at this property, typically you imagine c to b between a and b. Don't let it bother you that that's out of alphabetical order. And effectively, what you're saying in that context is the total area under the graph from a to b is the sum of two smaller areas. The area from a to c plus the area from c to b. The sum of these two areas gives the total area. Should make good intuitive sense. But this equation works even when your graph goes below the axis, which it did for this example, and some of my integrals were negative. The property still works. It even works, amazingly, if C is not between A and B. It works if C is over here to the right of B or over here to the left of A. It still works in the exact same way it's written. Though in that situation, you might also have to use property 2 to help you understand what's going on. Because if C is less than A, then the integral from A to C is one of these integrals. C is over here, less than A. That integral from A to C is really from a bigger number to a smaller number if C is over there. So you'd have to think about it that way with the negative sign in front of the integral from C to A. These properties may feel like they don't have much meaning to you at the moment. It's because you haven't had much experience with them. Are there situations where this is useful? Yeah. Sometimes it might be easier to do these integrals than to do that integral. Directly, at least. Maybe your function f of x is piecewise. Maybe it's linear over here and then quadratic over here. Does that happen? Sometimes. It'd be easier to do the integral of the linear part first, then the integral of the quadratic part second, and then add the results to get the total area under the curve. It's also got a lot of significance to statistics. If you've had statistics, finding areas under bell-shaped curves, normal curves. I mean, it's easily done with technology these days and not having to use this property. But before the technology, people had to use tables. And you can only make tables of areas under normal curves so big, otherwise they take up many, many pages. You want to make them in such a way that people can just use this property and still do many of those areas. Areas under bell-shaped curves are super important in applications in statistics. Fourth property, you could use the same name as our old friend, linearity. We've seen linearity before with derivatives, right? The derivative of the sum of two functions is the sum of their derivatives. d dx of f of x plus g of x is f prime of x plus g prime of x. You've used that unconsciously for about a month and a half now, 2 months. Anytime you take the derivative of a polynomial, you're using that. Also, constants can be kept where they are, constant multiples. Works for integrals too. The integral from a to b, I could write f of x plus g of x here. I could write f of x minus g of x. I'm going to write a more general expression. Say c1 f of x plus c2 g of x, where c1 and c2 are constants, numbers. Is c1 times the integral of f plus c2 times the integral of g. That's a linearity property. If I replaced the integral symbol with a d dx symbol for derivative, effectively I'd get the same kind of thing. I'd get c1 times the derivative of f plus c2 times the derivative of g. But it works with integrals too. Fifth property is if you've got a function stuck between two values for the outputs, meaning the graph of the function is always between two horizontal lines at little m and capital M. There's your function. Let's say A is here and B is here. So we're assuming this is true for all x in the closed interval from A to B. Then the integral, this area right here, is going to be between two other areas. It'll be greater than or equal to the area of this small rectangle here, and less than or equal to the area of this big rectangle here that I won't shade. What are the areas of those two rectangles? Base times height. In both cases, the base is b minus a. For the small rectangle, the height is little m. For the big rectangle, the height is capital M. The area of the little rectangle is less than or equal to the area under the curve is less than or equal to the area of the bigger rectangle. What's this good for? It's good for approximating areas under curves, approximating integrals, when the FTC is not super helpful because maybe you can't find the formula for capital F. That's what it's good for. Though if your function oscillates wildly on the interval, it's possible these two numbers could be very far apart. And so the integral, saying the integrals between them is not super helpful. It's more helpful when the function doesn't oscillate very much, doesn't change very much over the interval from a to b. That's when this is more helpful. You can generalize property 5 a little bit to property 6 to compare two functions. If f of x is always less than or equal to g of x for all x in the closed interval from a to b, then the integral of f, I hope it's not surprising, is less than or equal to the integral of g. If these graphs are both above the horizontal axis, there's f of x, here's g of x, well, yeah, the area under f is going to be smaller than the area under g. But once again, this inequality works even if f and g both go negative, maybe sometimes positive, sometimes negative. As long as you know the graph of g is above the graph of f, you can say the integral of g is above the integral of f. I said it the other way around that time, but that's okay. The seventh property is going to have two parts to it. I'll call it 7a and 7b. And this is out of order from your book. If f of x is an even function, so what does that mean? It means f of negative x equals f of positive x for all x. And realize that even though I said negative x could be a positive number if x itself is negative. Such functions have symmetry in their graphs about the y-axis. A generic graph of such a function. Graph the parts, say, to the right of the y-axis first. The graph to the left is going to be the mirror image. Something about like that. The conclusion is, if you integrate such a function from, say, negative a to positive a, then the integral from negative a to positive a, the area under the curve is, well, you could break it into two parts, the integral from negative a to 0 plus the integral from 0 to a, but by symmetry, these two areas are the same. So I can just double either one of them, and the convention is to pick the one on the right. 2 times the integral from 0 to a. When is this helpful? The most common place I see this used is in something called Fourier series. Fourier series. An advanced topic where you have infinite sums, series of trig functions. What? Infinite sums of trig functions of different frequencies. And you'd like to use these infinite sums of trig functions to model lots of situations, especially, for example, telecommunications. Analog signals is different than digital. This is more valuable before digital. Analog signals like radio. Fourier series is the basis for how you make radios. Of course, there's other things that go into it too, electronics and that kind of stuff. But mathematically, it's the basis of signal processing. Yeah. How do the radio waves get converted into something you can hear? It's partially this. I mean, there's other things too. There's your speakers and stuff like that. Yeah, I'm not going into the electronics of it. 7b is if f of x is an odd function, so f of negative x equals negative f of x for all x. What does a generic graph of an odd function look like over an interval from negative a to a? It's going to have origin symmetry. The graph's got to go through the origin because f of negative 0 will be negative f of 0. Negative 0 is 0. F of 0 has got to be negative f of 0, so therefore f of 0 has got to be 0. I said that really fast. Maybe you were not listening. The clock on my phone here says 50 minutes and 30 seconds when I was saying those things. If you feel like re-listening after class, the graph over here is going to look about like this. Mirror image. The area to the right of 0 is effectively canceled out by the area to the left of 0. These two areas cancel each other out by symmetry, and these two areas cancel each other out by symmetry. The integral from negative a to a is 0. All this is so helpful with Fourier series. When you got an odd function, this is such a time-saving device when you're doing things by hand. That integral's got to be 0. It's not the same as this property here, but it's still the same end result.